In the above solution, we assume that the union-find data structure has been implemented, but in this section, we provide a complete solution with an optimized implementation of union-find data structure. So, be optimized in the find A interface, we apply the path compression optimization, and in the union A and B interface, we apply the union by ranking A and B, which one is bigger. We just combine the small one into a big one. So in this table, we show a list of logs in chronological order where each entity indicates that the moment when two people become friends. So to visualize the final relationships, we draw the graph where each node represents an individual and the links between nodes which represents the friendship relationship between the two individuals. So in addition, the label on the top of the link indicates that the moment when two individuals become friends. So as one can see, on the timestamp 4, eventually everyone gets to know each other. Note that the connections 3 and 5 do not contribute to the overall connections among the friends, so they are redundant connections as we discussed before. So to highlight them, we just mark the connections with a dashed line. So how is our union find algorithm works? Initially, we have 4 groups where each individual is a group itself. So we use a directed link to point to the group that an individual belongs to. We start from the first event 1AB. We merge the groups of A and B together with the union A and B function. By merging it, we assign the group of either A or B to another one. So as a result, the merged group A and B contains 2 elements. So the total number of groups is now reduced to 3. With the event 2BC, we then merge the group of A and B with the group of C together. So to optimize the merging operation, we merge a smaller group into a larger group. So a smaller group is the one with a smaller rank value. So therefore, we merge the group of C into the group of A and B, and in the total of number of group is now reduced to 2. The keen observer will notice that C will actually point to A because of the effect of union by rank, but the main point here is that C has now joined the group with A and B. So for simplicity, we just point C to B. So with the event 3AC, as it turns out, the individual A and C is actually belongs to the same group. So therefore, no merge operation is needed. So the landscape of the group is remaining the same. So finally, with the event 4CD, we merge the group of D into the group of ABC. So now the total number of group is reduced to 1, and this is the earliest moment when everyone becomes friends. We create a new class, union find, and then we define the initialized constructor. We have self and size. We create a list group where each individual of the list is an integer starting from 0 to size -1 in this order. So it is used to store the group information for each individual. Well, the index is represent the individual and the value of that index, which is represent the group ID of that individual. So when the union find is initialized, all individuals are considered as a separate group. So each individual is assigned a unique group ID. The rank variable is refers to the height of the tree, which is used to represent the group. Specifically, the height of the tree is rooted at a given element, and the height of a tree is the number of edges between the root node and the furthest leaf node. So in other words, it is the maximum level of the tree counting from the root node. So in this implementation, the rank list is used to store the height of each group represented by a unique group ID. So when 2 groups are being combined, it is help us to determine which group to merge to keep the height of the tree as low as possible. So when we union by rank, we just merging the group with lower rank to the group with higher rank. Or we just merge the group with equal rank by increasing the rank of resulting group to ensure that the height of resulting tree is as low as possible after each merge. So in this way, the time complexity for finding a group for a particular element is O of log of n in the worst case, where the n is the number of elements. We create a list with size number of elements, where all elements are initialized to 0. So size is the number of individuals that passed an argument to the constructor when an instance of union find class is created. So this list is used to store the rank of each group, where index is represent the group and value at that index represents the rank of the group. As per implementation, rank refers to the height of the tree, which is used to represent the group. So it is initially set to 0 for each group, representing that all groups are having the same height initially. So during the merge operation by union, rank is used to keep the height of a resulting tree as low as possible. And then let's define the union function, which have two arguments, the node A and node B. So first, let's create a variable group of A, which is we try to find the group ID of A, and the group of B is we try to find the group ID of B. Let's try to define our find method, which have an argument person. So if that person is not the group leader, in that case, we try to recursively to use the find method to find the group leader and then assign them to group a person. And then after it becomes group leader, we just return the group leader as our group ID. IsMerge is a Boolean variable that is set to false before the if statement. Then the isMerge variable is checked when two elements pass to union method. If friend A and friend B already belong to the same group, then the isMerge is set to false. The function immediately returns. And if they are not in the same group, then the isMerge variable is set to true, which indicates that the merge operation has occurred and the union method continues. The two elements, node A and B, pass to union method to check if friend A and friend B already belong to the same group. If they belong to the same group, it means that they are already connected and no merging is required, so we return false. And the check optimizes the algorithm by preventing redundant merging operations. If without the check, the algorithm would unnecessarily merge groups that are already connected, which will slow down the overall performance of the algorithm. So now, let's try to compare the rank of groups. There are three situations here. The first situation is if group A have the higher rank, and then L if group B have the higher rank, and else if group A and group B have the same rank. So let's look at our first situation. If group A have the higher rank, we just merge group B into the group A. And if group B have the higher rank, we just merge group A into the group B. When the rank of the two groups being merged are equal, when the two groups with the same rank are combined, the resulting group's rank is increased by 1. Because when we merge two trees of the same height, the resulting tree will have one more level than the original tree, so the rank of the new tree should be updated to reflect the increase in height. So the merge is done by making the group A as the child of group B, which is done by making group A's ID equal to group B's ID. So this is done by updating the value of the index representing group A in the self.group list to be the value of group B. Let's analyze the complexity. Since we have applied the union find data structure in our algorithm, we'd like to start with a statement on the time complexity of that data structure. So if we have n operations, either union or find method are applied to n elements, so the total runtime is O of n multiplied by alpha of n. Well, the alpha of n is the inverse argument function. So in our case, the number of elements in the union find data structure is equal to the number of people, and the number of operations in the union find data structure is up to the number of logs. So let's say n is the number of people and m is the number of logs. So first of all, we sort the logs in the order of timestamps. So the time complexity of the quick sorting is O of m multiplied by log n. Then we create a union find data structure which take O of n time to initialize the array of group IDs. We then iterate through the sorted logs, so at each iteration, we invoke the union A and B function. So according to the statement we made, the amortized time complexity of the entire process is O of n multiplied by alpha of n time. So to sum up, the overall time complexity of our algorithm is O of n plus m multiplied by log of m plus m multiplied by alpha of n time. The space complexity of our union-defined data structure is O of n space because we keep track of the group ID for each individual, and the space complexity of our sorting algorithm depending on the implementation of each program language. So for instance, the list of sort function in Python is implemented with the team sort algorithm whose space complexity is O of n, while in Java, the array sort is implemented with the variant quick sort algorithm whose space complexity is only O of log of m. So to sum up, the overall space complexity of the algorithm is O of n plus m space for Python and O of n plus log of m space for Java.